Alrighty, in this video we are going to be talking about absolute and conditional convergence. So essentially the goal here is if we know that the series is convergent, we want to look at what's happening whenever we take the absolute value of each term and see if the absolute value of the absolute value of the series, is it convergent or is it divergent? So the first thing that we need to do here is prove that the original series is convergent. We can't really use absolute and conditional convergent unless you know that the original series is convergent. Now, once we know that the original series converges, what we're going to do is take the absolute value of the series, and we are going to look at that, and we're going to look at whether it converges or diverges. If we know that the absolute value of the series converges, then the original series is absolutely convergent. That just basically means that you know that no matter if you take the absolute value or not in that series, it's always going to converge no matter what. Now, if you take the absolute value of the series and it turns out it is divergent, then the original series is going to be called conditionally convergent. That just basically means that the original series is convergent, yay, yippee, hooray, but the series, if we were to add all of the terms up in absolute value, that is not going to be convergent. Now, most of these applications are going to be related to, of course, AST, obviously. So the first thing that we're going to do with 9, 10, 11, and 12 is make sure that AST holds, aka AST works. Because if AST doesn't work, then we can't really do absolute and conditional convergence. All right, so the first thing that I'm going to do is go ahead and take the limit of this. 1 over n squared is 0. And then at this point, if you want to prove this, we are probably going to do this. 0, negative, negative. That's enough information for me to prove that the terms are always decreasing. The terms are always decreasing. So at this point, you know that the original series converges. I'm not going to write down the whole statement just because I don't have space, but on the FRQ, you probably want to say that. So now what we're going to do here is just take the absolute value of the series. So now we have this in rad. Now, because the absolute value series is a p-series and our exponent is greater than 1, we know that 1 over n squared, the series for 1 over n squared, converges by p-series test. Because 2 is greater than 1, you want to tell me why you know that it converges by p-series. And because we know that the terms are always decreasing and because we have the p-series test right here, then we could say, therefore, the original series is absolutely convergent. So whenever we do this, we essentially have 2 tests to do. The first test is going to be the main test, aka, in this case, the AST test. So I don't think I'll put anywhere that the original series converges. So you probably want to write that down somewhere, that therefore the original series converges. And I know it's kind of implied with the statement in green right here because it's the same series, but we know that it just converges. We don't know if it absolutely converges, aka it always converges, or if it is conditionally convergent. All right, we're going to do the same thing with number 10 here. We're going to take the limit of this. The limit as n approaches infinity of n over n squared plus 4. That's approaching 0, so that's great. And then I'm not going to prove this. I'm just going to look at this, and we're going to pretend that this is decreasing right here. We'll probably look at this on Desmos and see if it's true. Oops, that's n squared plus 4. Okay. So just like the problem that we had on number 2 here, we are increasing a little bit from 1 to 2, but after 2 we are decreasing. So in this case, we're just going to pretend that the terms decrease in absolute value. All right, so we know that, therefore, the series, the original series, converges. All right, so what we're going to do now is look at the absolute value, and that's just going to be this right here, n over n squared plus 4. And we are going to look and see what's happening here. Now, of course, whenever we look at this, we could probably think about how we could use a comparison now in terms of compare with n over n squared, aka 1 over n. And because 1 over n is a harmonic p-series that diverges, that means that n over n squared plus 4 also diverges. So we're going to say that n over n squared plus 4 diverges by p-series comparison. Now, because we know that the absolute value, oh my Buddha. Because we know that the absolute value of the series diverges, but we know that the original series converges, this tells me that my original series right here is conditionally convergent. So this right here is conditionally convergent. Conditionally convergent. All right, number 11. The first thing that I'm going to do is go ahead and take my limit. That's just going to be 0. This right here is going to be 1 over n to the 3 halves. This right here, my terms are decreasing. I'm not going to prove it. Terms are decreasing, which means that the original series converges by alternating series tests. Yay. Once we do that, we need to see if the original series is always convergent or if it only converges conditionally. So now what we're going to do is take the absolute value of the series, and then we are going to look at this and say that, okay, that's the same thing as 1 over n to the 3 halves, which means that this is a convergent p-series where 3 over 2 is greater than 1. since we know that this is a convergent p-series, then we could say that the original series absolutely converges. Whew. All right. Looking at number 12 here, we're going to do the same thing. So the limit as n approaches infinity of 1 over n to the 1/4, that's going to be 0. Terms are decreasing. So the original series converges by AST. And then what's going to happen is, speed it up. We have n to the 1/4, which diverges by p-series tests. Since 1/4 is less than 1. Therefore, the original series conditionally converges. All right, whenever we look at something like number 13 here, where we have cosine over n square, the first thing that we're going to do is probably figure out, is cosine over n square convergent or not? So we are essentially going to compare this. Compare with 1 over n square. We know that cosine over n square is going to be less than 1 over n square. And because we know that this right here converges by p-series comparison, we know that this here converges by p-series comparison. Now, here's even better news. If I were to take the absolute value here, that cosine of n, instead of the outputs going from -1 to 1, it's now going from it now goes from 0 to 1, which really doesn't make a difference. So here, we could just automatically say that absolutely converges by p-series comparison. Probably going to prove that this converges. So converges by p-series. There. Same thing with number 14 here. I'm going to compare this with 1 over 2 to the n. And this right here converges by geometric series test, with r being 1/2. Which means that this right here, my original series, converges by comparison. And then if I take the absolute value, once again, -1 to 1 now changes to 0 to 1, which really doesn't make a lot of a difference. So here, sine of n over 2 to the n absolutely converges by geometric series comparison. All right. In the next video, we'll talk about alternating series error and what that is right there.